Hello. I wanted to do this example and also give you some geometric point of view for this one. So let's take S to be the set of three vectors in R3, 1, 2, 3, 4, 5, 6, 7, 8, 9. And you want to know what does span of S look like. So let's go to the geometric point of view. So let's try to look at this in a 3D. Okay. So here we have three-dimensional space, and I'm going to zoom in so we can see a little bit better. And here's the vector 1, 2, 3. Here's the vector 4, 5, 6, and here's the vector 7, 8, 9. It might be a little bit hard for you to tell. I'm going to move it around in just a minute. But here the red axis is the x-axis, the green axis is the y-axis, and the blue axis is the z-axis. So I'm going to move these around so you can see them better. So there they are. And what we notice is when we move these around, we notice that these three vectors all seem to lie in the same plane. You see that? They all seem to lie in the same plane. And so what we should expect is that our span is actually just going to look like a plane. I said in class that subspaces, and this is a very important subspace, the idea of a span, they can be the zero vector, they can be a line, they can be a plane, or they can be all of R3. So we should expect this one to be a plane, which means that it's not all of R3. Okay, so let's see how we would do this algebraically. Okay, so the question we want to answer is, what vectors are a linear combination? What vectors are linear combinations? I think I messed that one up. I should say are linear combinations of 1, 2, 3, 4, 5, 6, and 7, 8, 9. Okay, that would mean they would be in the span. And this is the same as saying for what B is C1, 1, 2, 3 plus C2, 4, 5, 6 plus C3, 7, 8, 9 equal to B1, B2, B3 consistent. Okay, when is that consistent? Notice now we're looking for the vectors B where this is consistent. That's what we're looking for what B is this consistent. So back in chapter 1, in order to be able to tell if we had a consistent vector equation or not, we would take these three vectors, we were calling them matrices then, take these three vectors, augment it with this vector, and say, when is it consistent? And it was consistent exactly when we did not get a leading one in the last column. So let's do that. Okay. So let's take 1, 2, 3, 4, 5, 6, 7, 8, 9, and augment it with B1, B2, B3. And now we're going to row reduce to see where we get our leading ones. We don't necessarily have to put this in reduced row echelon form. We can just put it in row echelon form to tell where our leading ones are going to be. So when I'm doing this, I've already got a leading one, and I want to get zeros underneath. So I'm going to replace row 2 with row 2 minus 2 row 1. And I'm going to replace row 3 with row 3 minus 3 row 1. And then I'm going to get this matrix here. Notice that we also had to manipulate the B's as well in that last column. Okay, so we're trying to row reduce. We see that we're going to get a leading one in that second column, Okay, so we want to get zeros beneath it. So now I'm going to replace row 3 with row 3 minus 2 row 2. And if I do that, I'm going to get the following matrix. Okay, so here we are. This is the matrix we get. And so in order for me not to have a leading one in the last column, remember that's what we wanted. We wanted this to be consistent. So no leading one in the last column. We need for this entry to be 0. If it wasn't 0, we'd have some statement that 0 equals something not 0. Okay, so we want this thing to be 0. So that's our requirement on B. We need that B1 minus 2B2 plus B3 to be 0. Okay, so this is a vector, and B1, B2, and B3 are the components of the vector. So if we think about this, then B2 and B3 could be anything at all we wanted, and then B1 would depend on B2 and B3. So when we think about, oh, B2 could be anything and B3 could be anything, that's like saying they could be parameters. So B2 and B3 are free parameters here, and so we would say B2 is free, so we're going to set it equal to a parameter, and B3 is free. It doesn't have to be the same thing as B2, it could be anything, so I'm going to make it a different parameter. And then B1 is 2 times the value of B2 minus the value of B3. Writing this as a vector, we would write it as 2t minus s, t, s, which I could rewrite as 2t, t0, just the t parts, plus negative s, 0s, just the s parts. Oh, I'm running out of room here. And I'm going to continue on the next page. So our B vector now is t times 2, 1, 0 plus s times negative 1, 0, 1, where t and s are real numbers. They're any real numbers. Okay, so the set of all B look like this. They are, notice what this looks like. They are a linear combination of 2, 1, 0 and negative 1, 0, 1. So B is a linear combination of 2, 1, 0 and negative 1, 0, 1. In other words, B is in span of the set 2, 1, 0 and negative 1, 0, 1. Which is really interesting because we started with the span of 3 vectors and we ended with the span of 2 vectors. Okay, so we could have the span of 3 vectors be the same as the span of 2 vectors. We're going to talk more about spans and when we can decrease the number of vectors in the span and when we can't, and what that means for us. Okay, but for right now, this is the point we've gotten to in the span example. Let me know if you have any questions, and I hope this helped.